Hi, today we're going to talk about the distribution of means, which is introduced in Chapter 5 of your textbook. And this becomes important because it becomes the comparison distribution for the statistical test that we'll be conducting in this class. So specifically, if you recall the 5 steps of hypothesis testing, in step 2 of hypothesis testing, we need to determine the characteristics of the comparison distribution. So this piece right here, the comparison distribution, to which we want to compare our sample mean. That comparison distribution in chapter 4 was a distribution of a population of individuals. So it was a distribution of scores from the population. That was pretty straightforward. In practice, when we conduct hypothesis testing, we usually want to compare our sample mean to a distribution of means as a comparison distribution. So we'll talk about that in today's lecture. So just to summarize, in chapter 4, the comparison distribution we used for our test was a distribution of scores from individuals in the population. The example here was the vitamin baby. If you look back into the last lecture, you can see that we walked through an example of a baby who was given vitamins to aid in development, specifically in walking age. And we compared that baby's walking age to the population of babies and how many months old those babies were when they started walking. So in chapter 5, we will be using a different comparison distribution, and that comparison distribution is called the distribution of means. And as I mentioned, this will affect us in step 2 of hypothesis testing specifically. So we're still walking through the same 5 steps to conduct our hypothesis test, but in step 2, you'll notice there will be some changes. So if we think about this logically, I'm just going to motivate this a little bit before we get into it. We have a sample of individuals from our study. So as the researcher, I collect data from a group of individuals, and I call that my sample. I have a score on whatever my variable is of interest. I have a score for each one of those individuals. And I could calculate a mean that is a representative value, a summary statistic, for my sample. So I calculate mean, and notice that we use capital M. Remember, we use the capital letter for the sample mean. If I want to compare that mean to something else in the population, what would it be reasonable for me to compare my mean to? If I want to know if my sample mean is large or small relative to the population, I can't compare my mean to a distribution of scores. Okay? Notice there would be a discrepancy there. I have a sample mean. I don't want to compare my mean to individual scores. Instead, I would like to compare my mean to other sample means. So I'm making sure that I'm using the same units here. The unit is a mean. So I want to compare my sample mean to a distribution of like things, and those like things are also sample means. Okay. And that leads us to a distribution of means. So that's the theory behind why we need a distribution of means for our hypothesis tests. Specifically speaking, definitionally, the distribution of means is a distribution that's based on a very large or infinite number of samples of the same size, n, and those samples get drawn from the population over and over and over again, and we calculate a mean for each one of those samples and create a distribution of those means. In this example, we'll say that we have a research question of whether people rate other individuals as more attractive if they believe that there's some sort of positive traits associated with that person. So for example, we could design a study where we tell people a positive story about an individual in a photo. So say they're looking at an individual, a picture of this individual that you see on your screen. And I could tell you This is a person who's so loyal. She's really good to her friends. She's kind, supportive. She always picks her friends up from the airport when they travel and never forgets her friends' birthdays. She always sends a warm text. So this is the kind of person she is. I want to know, or I have a theory that if people know about this woman and all of her positive characteristics, they will rate her as physically more attractive than if they weren't told anything at all. So that's my theory, and I'll design a study where I give Sac State students this photo, and I tell them a positive story. I tell them what I just told you about the individual in the photo, and I ask them to go ahead and rate her attractiveness on a scale of 0 to 10. I recruited 64 students from Sac State for my study, so my sample size, or N, is 64. Alrighty, so if we think about this theoretically, I could say that I now have 3 distributions that I could distinguish between. I could think about a distribution of my sample scores. So all my 64 students rated this photo and gave the person in the photo an attractiveness rating of 0 to 10. So I have all those 64 scores, and I could put them on a histogram to view the distribution. Okay. So that is my sample distribution, the distribution of sample scores. I also could think about, theoretically, the distribution of attractiveness ratings for all of my population of students at Sac State. So if my population of interest is students at Sac State, then there's theoretically a distribution of all those students' attractiveness ratings, right? The ratings they give to the person in this photo. Usually I don't have that information. It's a theoretical distribution. I don't actually collect, remember, data from the entire population because I'm taking a sample instead. All right, so I have my sample distribution and my population distribution. The third distribution that we're introducing in Chapter 5 is called the comparison distribution, or the distribution of means. And the distribution of means is, in this case, going to be theoretically a distribution of means of samples that I draw over and over and over again from the population. So, for example, what I'm doing here is I'm going to my population at Sac State students. I reach into my population and I get 64 students for my sample. I ask those 64 students to rate this photo for attractiveness, and then I calculate a mean for that sample, a mean rating. And I'll tuck that aside over here, I'll save it. And then I go back into my population of Sac State students, find another 64 people, ask them to rate the same photo, calculate my sample mean for that sample, and I'll save it over here to the side. Okay. And I keep doing that over and over and over again. I'm sampling from the population with sample size N, which is equal to my original study sample size. So in this case, 64. Notice, so I'm going in, taking 64 students, calculating the mean and saving it. 64 students, calculate a mean and save it. Okay. So I'll do that iteratively over and over and over again until I have a whole bunch of scores over here, or a whole bunch of values that are all just means. Okay. And I could think about building a distribution or creating a histogram of those means. That distribution is called the distribution of means. And each of these distributions, the distribution of scores, the distribution of the population values, and the distribution of means, has a mean and a standard deviation. Okay, so now we're talking about the whole distribution has its own mean and its own spread, or how much variability exists in that distribution. So, for example, my sample of 64 students at Sac State, that's my data, right? There's a mean score for my sample, and I can calculate the standard deviation of the score for my sample. That's pretty straightforward. There's also theoretically a population mean. And remember, that's denoted by the Greek letter mu. That's this right here. So the population mean is the Greek letter mu. And the population also has a standard deviation, which we denote by sigma. Remember that we could also distinguish between the population and the sample variances, which would be SD squared and sigma squared, respectively. Those are the variances, right? So when we get to the comparison distribution of the distribution of means, this distribution also has a mean and a standard deviation. And the mean of this distribution will be denoted by mu sub m. So we know mu always will represent a mean. And in this case, this is the mean of the distribution of means, which is why we have mu sub m. And then similarly, sigma sub m will be the notation we will use for the standard deviation of the distribution of means. So notice the things here to pay attention to are the different notation that we'll be using for these three different distributions. So m is different from mu, is different from mu sub m, right? And noticing the difference between those things will be really important. So remember I said that this becomes important for step 2 of hypothesis testing. When we get to step 2 of hypothesis testing, the language in that step says, determine the characteristics of the comparison distribution. So in this step, we will need to figure out what is the value of mu sub m and what is the value of sigma sub m. So we need to know its mean or centrality. We also need to know its spread. Okay, that's the variance or the standard deviation. And we thirdly need to know the shape of this distribution. So those are the characteristics of the comparison distribution. Those characteristics can be calculated with information we already have in our toolbox. So in our toolbox, we have the characteristics of the population distribution, and I also know my sample size n. And just with those pieces of information in our toolbox, we will be able to determine the characteristics of the distribution of means. So we are going to learn some basic rules for how we can use the information from the population distribution to determine the characteristics of the distribution of means. The first rule is that the mean of these two distributions is identical. So that's really easy. Try to just remember this piece of information, that mu is equal to mu sub m. Okay, so the mean of the distribution of means is exactly the same as whatever you know the mean of the population to be. Also, the second rule of the distribution of means is that the spread of that distribution will be less than the spread of the population distribution. We expect the spread of the distribution of means to be smaller. Notice here that it has less variance, so it's narrower, right, compared to the population distribution. It's narrower because it's a distribution of means, meaning that when I go in and I sample over and over and over again from the population, each time I sample, I get 64 scores that could be all over the place, right? Some of those scores might be really high, some of them might be really low, but then I take the mean, which is basically like a middle value, right? And then I'm only saving that. I didn't save the original extreme scores, I only saved the mean for that sample, and I tucked it away. Then I went back into the population, sampled again another 64 individuals. Again, those scores might be really extreme. They could be very variable, really low ratings, really high ratings, but then I suck it all into a sample mean, and I only save that value. So because In this process, I'm only saving basically the middle values. I'm saving the mean, one representative value for each sample. I'm getting rid of those extreme values. I'm kind of weeding out and cleaning up all those extreme values and only hanging on to sample means. So then when I create a distribution of those sample means, it's not going to have as wide of a spread or as much variability as the original scores. Okay, and thirdly, the third thing we know about the distribution of means is that its shape will be approximately normal if the sample size is greater than 30. Okay. It will also be normal, approximately normal, if the population distribution is known to be approximately normal. So that's in this note here. You see normal if the population is normal, or regardless of the shape of the population distribution, this distribution will still be approximately normal as long as sample size was about 30 or more. Okay, so these rules can be rewritten as you see here, right? So I see mu sub m is equal to mu. And remember the notation, mu sub m is the mean of the distribution of means. Mu is the mean of the population distribution. I also know that sigma squared sub m, or the variance of my distribution of means, that's this, variance of the distribution of means, is equal to the variance of the original population divided by sample size. And this is an adjustment we make. Someone came up with this formula to adjust for the extreme values. So we know that we want to shrink down the variance from the population distribution to the distribution of means, okay? Because on our previous slide, as I showed you, the variance should be smaller. It's expected to be smaller in the distribution of means. So here we make a correction to the population variance term by dividing by n. And that correction will get us a slightly smaller but related term for the variance of the distribution of means. And as always, I know that the standard deviation and the variance are related. Right? The variance is just the square of standard deviation, or in other words, that the standard deviation is the square root of variance. So once I calculate my variance of the distribution of means, I can take the square root of that value to get my standard deviation of the distribution of means. And I know finally that the shape will be approximately normal, or I need the shape to be approximately normal, and it will be as long as the population is approximately normal, or as long as my sample size is greater than or equal to 30. In this case, the standard deviation has a special name. It is the standard error of the mean, which sometimes you'll see called the SEM, but often we call it just the standard error. So the standard error is sigma sub m is the standard error. So from now on, if you hear me referring to the standard error, I'm talking about sigma sub m. So let's go back to our example. If I know that CSUS students or Sac State students in general at the population level rate attractiveness of others with a mean of 5 and a standard deviation of 2.58. So in other words, I know that mu, the mean of the population, is 5. I know that sigma, the standard deviation of the population, is 2.58. And if I square sigma, I get the variance, which is 6.67. So So that's what I'm starting with. I also know that my sample size was 64, right? I sampled 64 individuals for my study from this comparison population. So now in step 2 of hypothesis testing, if I actually wanted to go through and see if my sample, after they're told really positive ratings of the person in the photo, gives them a higher attractiveness score than the average student at Sac State, then I need to consider the characteristics of my comparison distribution. So I know the characteristics of the comparison population, but my comparison distribution needs to be a distribution of means. So how can I get the characteristics of the distribution of means from this information that I know already about the comparison population? I will use these rules that I have in the boxes here. So I know that mu sub m, the mean of my distribution of means, is equal to the mean of the comparison population. So in other words, I know that mu sub m is going to be equal to, I hope you're thinking 5, right? It's going to be equal to mu, which we know over on the left-hand side of the slide is 5. I also know that sigma squared, or the variance of the comparison population, is 6.67. That value divided by the sample size will get me the variance of the distribution of means. So I know that the variance of the distribution of means, sigma squared sub m, is equal to 0.104. Now, finally, I need to compute the standard deviation of the distribution of means. In other words, the standard error. To get to the standard error, I can just take the square root of the variance of this distribution, okay? So sigma sub m is equal to the square root of 0.104, okay? Which is going to give us a value of 0.322. So 0.322 is the value of the standard error. And finally, I need to ensure that the shape of this comparison distribution is approximately normal. And the shape of the comparison distribution is approximately normal if I know the population to be normal, or if my sample size has at least 30 individuals. So in this case, my sample size is 64, right? I'm good to go ahead and say my distribution of means should be approximately normal. You might be wondering why that matters, and it's because we will be doing our whole hypothesis test using that distribution, and we need it to be approximately normal because that's how we know what proportion of values fall under different areas of the curve. Or if you think back to one of my previous lectures, I talked about how all hypothesis testing is founded in probability, right? So I know exactly the probability of my test statistic occurring as long as it falls on this normal distribution. So if I can map on my sample score onto this comparison distribution, then I can figure out exactly how likely or unlikely my value is, my sample value is, as long as this distribution is normal. Alrighty, and that's all I have for you today. Remember that there's opportunities for office hours on Wednesdays from 10 to 12:30 in the morning, and those can be accessed via Zoom. And you can find more information for that on Canvas. Okay, good luck.